Hey guys, I'm going to go through a two-dimensional projectile motion question, also commonly known as the cannonball question. And in this scenario, what I'm going to be looking for is where does the cannonball land? I'm launching a cannonball from this cannon up here on top of a cliff or a castle wall or whatever it is. I'm going to throw some numbers on here and we'll go through this solution in three stages. Let's start with some numbers. I'm just going to say this thing is, say, 50 meters tall. That's how tall the cannon's initial position is. I'm going to launch this cannonball at a particular angle. I'm going to say, let's just say it's 30 degrees to the horizontal. So this is 30 degrees. And we're going to launch it at an initial velocity of 100 meters per second. Okay. Now, in order to solve this problem, what's going to happen here is the cannon's going to be launched and the ball's going to go out like this and eventually come to land somewhere over here somewhere. The question is, how far is it from here to here? That's what I want to know. Okay. So the three phases that we're going to go through is the first phase is going to be um, decomposing the diagonal of this initial launch direction into a horizontal component and a vertical component. Once I have those two velocities, I'm going to then write an equation for the position of the horizontal and the vertical position of the cannonball itself while it's in motion. And then finally, in the third phase, I'll go ahead and solve and figure out where the thing is going to land. So the first thing I have to do is understand that the two components of motion, horizontal and vertical, act independent of one another. So no matter how fast it's moving horizontally, that has no effect on how fast it's going to move up and down. And the same is true of the up and down, doesn't have any effect on how it's moving horizontally. Now, when I talk about the motion of an object in two dimensions, it's difficult to talk about it in terms of a diagonal, like this thing is initially being launched. So what I want to do is I want to figure out how much of this 100 meters per second is acting in the horizontal direction and how much of that 100 is being acting in the vertical direction. So let's start with that. This is phase one. So I start with the launch of this cannon at 100 meters per second, and I want to draw a triangle so that the horizontal axis here is going to represent the velocity, the original velocity of the cannonball, that's what velocity original, in the x direction, and then the vertical part of this is going to be the velocity, the original velocity, in the y direction. And of course, the 100 was the original velocity in the first place. Um, the velocity of the ball may change as it's in flight, but the velocity with which it was launched remains the same. That was 100, and then after it's launched, it can change and do whatever it was. But what we're concerned with right now is the original velocities. So I have a triangle here. I also know that this is a 30-degree angle. Okay, obviously the black part here, this represents the initial launch of the cannonball, and let's start with I guess we'll just do the red one. That will be the horizontal component of its velocity. When you look back at SOHCAHTOA, we have a right triangle here. I hope you can recognize that this is the opposite side, and this is the hypotenuse, and this is the adjacent. So I want to dissect this thing into, I want to be more concerned with the red x velocity and then later the green y velocity. So let's talk about the x first. Anyway, I would say that cosine of 30 degrees is the adjacent over the hypotenuse, which is 100. I can do a quick little cross multiply here and get 100. Cosine 30 is the velocity in the x direction, and I can calculate that to be 86.6 meters per second in the x direction. Separately, I'll work on the y direction, same triangle, but this time I'm going to use sine. So I'll say sine of 30 degrees is going to be, in this case, the opposite, which is this side here, the y. The opposite over the height. So I'll say this is the velocity in the y direction over the 100, which is the original velocity, the black one. We cross multiply, and I got 100 sine 30 equals velocity in the y direction. I can type that in my calculator, and I get 50 meters per second is the velocity original in the y direction. Now that's step one, that's phase one, and depending on how the question is given to you, you're going to have to one way or another resolve the diagonals, any diagonal that you have, into a horizontal No, that's not what I meant. Horizontal and also a vertical. Now that we have those, we can move to phase two and actually plug them into equations. Let's go to that. Okay, so this is probably the most important part of the solution to this problem, is writing these two equations. Once again, it's critical to remember that the way this thing moves horizontally is completely independent from the way that it moves vertically. So we have two separate equations. Each of these, they're both the same equation. They both have the same components to it, but we'll put different numbers on depending on what effects are taking place in the x direction and which ones are taking place in the y direction. So let's go through each of those two things. So back on our diagram here, I'm going to consider this to be the y-axis. I'll make this to be the zero position for x. Of course, this is the x-axis. We'll count in this direction. This will be the x-axis here. And we're counting, 1, 2, 3, 4, 5, 6 meters, however, and we're trying to figure out where this thing's ultimately going to land. So let's go, I suppose we'll do the horizontal one first, all right? When I look at the three pieces of this equation, this is the acceleration that's acting on the object. I'm talking about after it's launched now, as soon as it leaves the cannon. That's the acceleration that's acting on it. This is the original velocity. The v is the original velocity. The x is the original position. So we'll go through each of those things. All right. So I'm calling this the x function because I'm talking about how it's going to move left and right. The variable here will be time. We'll measure that in seconds. So it's x as a function of time equals 1/2. That's part of my equation. The acceleration in the x direction. Now here's the thing. After it's launched from the cannon, so after it leaves this cannon right here, the ball then at that point is flying on inertia. Left and right, there's nothing pushing it anymore. The cannon pushed it to the end of the barrel there, and after that, it's kind of on its own. There's nothing pushing it forward any further. There's also nothing pushing it back either. We're going to disregard the air resistance or the wind that might be, keeping it from flying. But for the most part, this thing is just flying on its own in the x direction. So the acceleration is not speeding up after it leaves the cannon. It's not speeding up anymore. It's also not slowing down at all, left and right. So the initial acceleration acting on this thing would be a 0. Okay, after it leaves the cannon, it speeds up through the barrel. As it starts way here at the back of the barrel, you have an explosion that takes place, and the ball speeds up all the way to the end of the barrel, and then it's on its own after that. So we have 1/2 acceleration there is going to be 0. Here's my t squared. That's always my variable that will stay. The next part is the original x velocity. Now that's the reason that we did this triangle bit back here. The original x velocity is of the 100 miles or meters per second with which this thing was launched. We found that 86 of it was designated in the x direction. So that is our original x velocity, 86.6 meters per second. There's my time. It's the next variable, plus sign. Now, this piece here, the original x position, the way I'm designating this, it seems to me that I should start counting from 0. X is 0, and then we'll count 1 meter, 2 meters, 3 meters, 4 meters, all the way until it lands. So I'm putting the original x position to be a 0. So that's right there. When I simplify this equation, I have x as a function of time equals this piece being a 0, it's going to be, 0 times t, no matter what the t is, it's going to be a big 0. The 86 is going to be there, 86.6 t. This 0 is gone anyway, so there it is. That's the entire x direction right there. It says that the position of this object is going to be 86 meters per every second. So if we wait for 1 second, this thing's going to fly 86 meters. If we wait 2 seconds, it's going to be 86 times 2, whatever it is. All right, now let's focus on the vertical. Now this one's a little bit different. We have the same three components. In fact, it's the same exact equation. The A stands for the acceleration that's going to be acting in a up and down vertical direction. The V stands for the original velocity, and the Y over here is the original height. Y is the vertical, so we're talking about, how high up it was in the first place. When we launched this cannonball, well, let's go through all three pieces. I'll start with, I made this green, so make it green. So y as a function of time. Okay, I'm actually going to start with this piece here. That might be the easiest one to explain. When this thing first left the cannon, it was already 50 meters up in the air. So I'm putting the original height to be 50. Now, I know you're going to give me a little hard time about this, but I'm disregarding that, all right? That little bit of the slant here, I'm not going to worry about that, all right? 50. We're going with 50 meters. This thing was 50 feet off the ground when it was launched. That's how tall the wall was, or the mountain, or whatever you launched the thing from. So that's my initial height right here, my original height, okay? I launched it. I'm talking about this piece now as my T. We figured out that it was launched at 100 meters per second in a diagonal direction. But remember, we decomposed this into x and y coordinates, finding that 50 of that, 50 meters per second, was acting in an upward direction. So there's a different 50. I should have chosen a different number. I didn't know it was going to turn out to be a 50. But anyway, two different 50s, all right? This 50 here is the original velocity, meaning that was going upward. Notice it is a positive 50 because its initial velocity was in an upward direction. Couple things about that. If this cannon had been horizontal in the first place and the cannonball was launched straight out like this, then the original velocity here in the y direction would be a big zero because it's not going up or down. When it first leaves the cannon, it's not heading up, it's not heading down, it's just heading straight across. Now, yes, sure, then gravity reaches up and grabs this thing and begins to pull it down, but that's the acceleration part. When it first leaves the cannon itself, it would be going only horizontal, in which case this would be a zero. That's if it was launched horizontally. For that matter, if for whatever crazy reason this thing had been launched downward like this, then this original velocity right here, that would be something negative. We'd have to, of course, decompose it to whatever, but it'd be something negative there because its original velocity would have been in a downward direction. That's what we designate up to be positive and down to be negative. So in our case anyway, this thing was launched at an upward angle like this, so some of its original velocity was designated in an upward direction. That's why we have a positive we found out to be 50. This scenario is pretty common when you launch it directly horizontal. And again, when that's the case, then this component is just a zero, and you'd move on from there. All right, now this piece here, we have the 1/2. Let's talk about the acceleration and then the time squared goes in. You see I'm just filling in this part of it here. Um, Vertically, there is an action being put on this object. Gravity is pulling on this, a force. There is a force of gravity which doesn't work left and right, which is why we didn't put it on this one. Gravity doesn't work left and right. Gravity only works up and down. And since we're talking about the up and down motion of this thing, this vertical equation here, acceleration comes from a force acting on the ball. And once the ball leaves the cannon, it's flying and gravity is pulling it down. So the acceleration of gravity is going to be negative 9.81 meters per second squared. That's an important number. It'll come up anytime you're doing a problem like this in physics. You'll understand that gravity of acceleration of gravity is known. It's a well-known number. It's always going to be negative 9.81 meters per second squared. That's metric. So let's put that in there. I'm going to simplify this a little bit. I can do 1/2 times 9.81, and I will put that down as 4.8. So let's just simplify this a little bit so that we have y as a function of time is going to be negative 4.8, 4.8 t squared plus 50 t plus 50. 4.9, I don't know what I'm saying here. 4.9 is what it should be, not 4.8. All right, there we are. Okay, so let's clean that up just a little bit. Okay, now this is the key. Having these two equations is critical. Once I have these two equations written, and you can see what it took a little bit of work to get these two equations, but once I have them, I can answer whatever question you want to ask. If you want to know, for example, where is the object going to be after, say 1 second, I would say, well, x after 1 second, you can plug in 1 second for all the x for the time in the x function. The x function. Find that it was 86.6 meters out. You do the same thing. Plug in 1 second for the y. It'll tell you that it's 95 meters tall. And just to show you what that looks like, back on our picture here, that would mean that after 1 second, the ball's somewhere over here, where it's at a height of 91 meters, 95 meters tall, and it's 86 meters from the it's 86 meters in this direction from the cliff, and it's 91 meters up from the ground. So it's at this place right here. I should put that right there. It's about there somewhere. Anyway, that's what that means, just as an example. Okay. Anyway, let's get back to the question we're trying to figure out, and that is, where does the thing land? Okay, so I said we're going to do this thing in three phases. Again, phase one was figuring out the velocities in the x direction and the y directions, two separate components. The reason I needed to do that is because I started with a diagonal. Again, if you had started with just a straight horizontal like this would be less necessary because you know all of the original velocity would be heading in the x direction in that case. That was phase one. The second phase of this was then to build our two equations. That was phase two. And now finally, we're going to solve these equations. Now, here's the thing. We're trying to figure out when the thing lands, like lands on the ground. And there's a hidden clue in that question. When it lands on the ground, somewhere over here, okay, we know what the height is going to be. So there's a hidden clue in that. When it lands on the ground, it means that the height would be a 0. That's a number that I can use back here in our equations. Where are we? If I want to know when the ball lands on the ground, I know that the height will be a 0. And the key here is, in order to know where the ball lands, you first have to know when it's going to land. So let's figure out when it's going to land. And in order to do that, I'm going to use the equation right here for its height. The vertical component of this thing is the height of the ball. And I know right now that I want to find out when time equals what, when the height equals 0. Or this is, the y. When does it equal 0? So let's focus on that for a moment. Okay, so we know that y equals 0. We want to know time equals what? All right, let's plug it in. We have 0 equals negative 4.9 t squared plus 50 t plus 50. We have to solve for t. I would say I'd love to be able to factor this thing to solve for it, but it's not going to work, so I'm going to have to use the quadratic formula. Let's see if you remember the quadratic formula. All right, this is how the quadratic formula is typically presented. So let's plug in our numbers and see how this looks. Now, in this case, instead of where the x position typically would be, we have time values instead. So I'm not going to use x equals, I'm going to use time equals. Negative b plus or minus, here, I'll just write it out. Again, I'm using t for time because that's the variable I'm solving for. And let's plug in our numbers. So the b is going to be the 50. I'm talking about this 50 here. Um, the A is our negative 4.9. That goes here, 4.9. And the C position here is a 50 as well. And let's run some numbers through. I put some numbers into my calculator. I got to this point here. Let's type in the square root of 3480, which comes out to be 58.99. Let's keep that. Okay, so now I have to continue to solve this thing. I'm going to use my plus and minus. We'll do it once as a plus, and we'll do it once as a minus, and we'll get two answers. Let's find out what those are going to be. So in my calculator here, I have negative 50 plus 58.99, and I'm going to divide that by negative 9.8. I'm cheating a little bit by putting the 9.81, but it's 9.81, we're calling it. And I'm coming up with an answer of 11.11. That would be seconds. Now let's see what I get for the other side here. I just did the minus version of that. Sorry about that. That belongs here. Sorry, I just did the minus version. Let's do the plus version. And when I do negative 50 plus 58.99, enter divided by negative 9.81. I'm coming up with negative 0.9165 dot 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 dot. Okay, so the question was, when does the cannonball land? And I would say that it lands at 11 seconds, 11.11 seconds. And what that means to our problem here is that this thing 11.11 seconds to fly. That's how long it's going to be in the air. It's going to be in the air for 11 seconds, and during that time, it needs to get as far as it can get. That's what's happening. It's going to be in the air for 11.11 seconds. The question is, horizontally, how far can it get during those 11 seconds? So we used our vertical equation to figure out how long it's going to be in the air, right, from until the time that it lands. We knew that the height then would be a zero, so I was able to plug in one variable, the zero, for y, and by doing that, I was able to solve for the time variable right here, 11 seconds. I know that this thing's going to fly for 11 seconds. So now let's bring it back to our horizontal equation and figure out um, in the horizontal direction, how far is it going to go before it actually hits the ground? So all I have to do here is find out its position after 11.11 seconds. It's going to be 86.6 times that 11.11 seconds. And when I plug that in, I have 962.126, and that would be in meters. X at 11.11 seconds. Okay, this is the answer to our question. From the time that it's launched, it's in the air for a total of 11 seconds, 11.11 seconds, and during that time, it travels 962 meters, 0.126, whatever. That's how far it goes. And now I know where the ball is going to land. And that's how you do a cannonball problem.